this is Lori, and welcome to my project on creating a color mixer for an RGB LED with a Raspberry Pi and Python. And in this project, we'll use 3 potentiometers to mix the red, green, and blue colors. We'll also need to have an analog to digital converter because the Raspberry Pi doesn't have one built in. So we'll be using an ADC chip also in this project. So here's the circuit that I intended to use for this project, using a Raspberry Pi and then connecting to an extension board to bring the GPIO pins onto the breadboard. And here's the ADC chip that I've been using from the Sunfounder kit we're using in Paul McWhorter's Raspberry Pi class. And then here are the 3 potentiometers that will control the red, green, and blue of the RGB LED. And you can see that's hooked up here with 3 current limiting resistors for the red, green, and blue colors, and then a connection to ground. So that was my intention, was to use this circuit. But that didn't work out. I was really struggling to get this to work and often getting kind of very strange results. And it got so bad that I thought, I don't know, maybe I just don't get this. And I decided to take everything off the breadboard and kind of start over again. I figured something must be wrong. I must have something miswired. And so I thought maybe if I start from scratch, I'll figure this out. Well, as I pulled off the ADC chip, I noticed that the pin had been bent as I pushed it into the breadboard when I put it on. It kind of worked, and so I guess a little bit of this leg was touching the breadboard contact occasionally, but it was clearly not working all the time, and that was clearly the cause of my problems. So I tried to carefully bend the leg back and put it back into the breadboard very, very carefully, and for a few minutes it worked, and then again it started giving very crazy results. And I touched it with my finger, and it almost burnt my finger. It was so hot. So that's what the flames are for. So I immediately pulled the power and pulled it off the board and said, well, that's obviously not going to work. So rest in peace, ADC7830. That's a dead chip. So I dug around in my box of goodies to see if I had another analog to digital converter, and luckily I had bought another kit when I first got my Raspberry Pi, and there was an ADC little board in there that I could use. So I switched over to this board. It's quite a bit different. The way you hook it up is actually a lot easier. There's a lot going on the board. It's an ADS7830. It's also an 8-bit chip, and it has 8 channels. So you can see that there's a lot less wiring required to the Raspberry Pi to control this. It uses I2C communication, so much simpler connection for me as the user. So that's what I did. I switched over to this chip that I had to try to complete this project. So a little bit about the ADS7830. As you can see, there's a little bit more going on. It's got quite a bit. That's the chip itself, but there's resistors. And the other thing I like about this is clearly I have some issues pushing things into breadboards. This is a much more breadboard friendly a chip for me. You can see it has nice little headers, so less chance of making a mistake like I did with the first chip. So it's still an ADC. It still uses successive approximation like the other one, but it uses I2C for communication. It has 8 input channels rather than 4, so that's kind of nice, but I only needed 3, so don't need the other 5. It also will run at 3.3 volts, so I don't have to give it 5 volts like I did the other one. So you'll see that when I pull the power off in my from the Raspberry Pi, I just use the 3.3 volt to power the board rather than the 5 volts. It does come with a driver from the kit that I originally got my Raspberry Pi with. But I looked around and did some searching to try to understand, how to use this particular chip. And I found some code that's pretty simple that uses the SM bus library, Python library. And I found a small, very simple function that was all I needed to add to my code so that I could read the values from this chip. And connecting up is really simple, as you can see. And there's just a ground connection and a power connection. So ground here at pin 9 and power up here at pin 16. And then the serial data line and the serial clock line have to be connected to the same pins on the Raspberry Pi. And they're up here in the second and third position here on that. So that was a little simpler of a connection. So I just went ahead and used the DuPont connectors because that didn't seem to be that complicated a circuit to have to make special wires for, so I didn't do that this time around. And so next we'll go through the code that I used and see how it works. I do want to mention that I did a previous video that talked about how analog to digital converters that use successive approximation, how they work, and how that algorithm works, and I will link that previous video in case anybody's interested in how successive approximation works. But now we'll go right to the code. First thing I'll do is import the needed libraries, and you can see I use the SM bus library to do the I2C communication. So we'll see where that figures into the program. And the first thing that we do is create a list of addresses for the 8 channels on the chip, and this just allows any of the channels to be used by the read function. So just a little list there of addresses. And important to use this chip, you need to have your I2C protocol enabled on your Raspberry Pi. If you haven't done that, you'll need to go into the configuration tool to enable that interface. So make sure you do that if you're going to use a chip that uses this kind of communication. And you can type this a command into the terminal to see if you have it enabled, because if you don't, you'll get an error. If you do have it enabled, if you have the chip all hooked up nicely, you'll actually see the address of this chip. So you can, that's a way you can double check to see, do you have the hexadecimal 4B, which should be the address of this chip. So this is the very small function that reads from that ADC, and it just uses this function write byte and bus read byte to do the communication. It's something that I got from another YouTuber, Heidenreich, I guess is how you say it. He has a nice channel with some very good information, and I got this function from him. Next we'll do, just like we always have, we'll use the BCM mode, and I was messing around with the delay time, but it could be very small. Right now I just have it at 0.5, but could be much smaller than that. And then we have to start the SM bus instance. Then just setting up the red, green, and blue pins all as outputs, and then 3 pulse width modulation objects for the red, green, and blue. Then I'm going to have 3 variables to contain the current duty cycle for each of those, and then go ahead and start them at 0. And then in the while true loop, here's where we'll use that new function to read from the 3 channels of our ADC. And I did leave in the code to do a linear change, but I kind of like the nonlinear change, so I did a previous video describing this, and I'll link it below as well. if anybody's interested, but this is the nonlinear equation I'm using to do sort of a nonlinear control of the potentiometer. And then I just double check to make sure I'm not going over 100 or below 0 when the duty cycle gets close to those two values. I just go ahead and turn it on or turn it off. And do the same thing for green and blue. And then I print things out so I can take a look and see what what the values are for the analog value coming in, as well as the duty cycle for the red, green, and blue in order there. And then the short delay time and go through the loop. And with the keyboard interrupt, we'll end the program and stop the pulse width modulation objects and do the GPI cleanup. So pretty simple program, very straightforward. So here's my setup. We'll do a quick flyby. Raspberry Pi, ribbon cable, extension board. There's the ADC, and the 3 potentiometers, and there's my RGB LED, and you can see that. I'll put my little cover there, so try to help the color show a little bit better on the camera. And here's the the ADC7830 that is no longer with us any longer. Rest in peace. All right. Let's kick this off, and you can see the output. So each pair of numbers there is the analog value and the duty cycle for red, green, and blue. So that's what we got going. So everything's off at this point. So now I'll just come in here and we'll start looking at it. I'm going to move it in just a little bit to try to maybe get it out of the bright light there. Maybe it'll help us see the colors just a little bit better on the camera. So let's turn on some red. You can see it going full on. And that's fully on. And I'll take it down. And then we'll watch the green come on. That's fully on, and we'll take it down. And here's the blue. Just show you what the printout on that would look like. So you can see the blue, and you can see the analog value and the duty cycle for blue. And of course the whole point of this was to be able to mix colors. So let me turn the blue down just a little bit, maybe about halfway, and let's turn on a little green here and see what we get. Very good. Alright, so maybe we'll turn that down and we'll go back to put some red in there, and now we can see a little bit more of a purple. So yeah, we can mix any color, and gosh, I wish it showed better on a camera, but works pretty well. So great project, and thanks for watching.